All right, so we've been considering the example shown here. We have a disc connected to a hanging mass through a pulley. The pulley is frictionless, but it's not massless. And then our disc rolls without slip. Gravity is included here. We're asked to determine the equations of motion. Last time we went and defined a coordinate system, we chose to use Cartesian at the center of the pulley. From there, we went to define position vectors for first the center of mass of the disc, and then second for the hanging mass, shown there. We then went and computed acceleration and velocity and then acceleration vectors. And now we're going on to do free body diagrams. All right, so we have here, we're gonna need 3 free body diagrams, one for the disc, one for the pulley, one for that hanging mass. We can start with the pulley, since it is the simplest. It's gonna have tension pulling it down, we'll call this T1. Tension on the other side, we call this T2. They're not necessarily equal to each other, and we will see when we go and apply Newton's second law, we'll see whether they end up being equal to each other or not. On the hanging mass, we have tension T1 pulling up, and then we have the force due to gravity. This will be M2 times G, and that's pulling it down. Now on the disc, we'll have some tension at the top, pulling it to the right. That is T2 here. We have gravity pulling it down. We call that, let me check. Should be M1G. And then there's applied force applied at the center here. That force is F of T. Then we'll have some normal force that pushes up. And then we'll have a friction force that goes to the left here. We'll just call that FF. All right, any questions on the free body diagrams?
Would you account for the gravitational force on the
Sure. So if we wanted to, we can account for gravity from the pulley. We can just say this is, what did I say the mass of the pulley is? M3G. And then there should also be some reaction force. We'll say R1 here. And then I'll just guess the direction for R2 as well, acting like that. So when we go into sum of forces equals mass times acceleration, with acceleration of the pulley, the translational acceleration of the pulley is 0 because it's pinned. And then you'll just use those equations to find the reaction forces. So the reason why I skipped that is because we're not interested in reaction forces, we're interested in the equations of motion. But since you asked, we'll go through and do it all, and we'll see how that all comes together. Since the pulley is pinned, we are generally just going to want to do some of the moments about that pinned position. Okay. In that case, this makes the block the simplest one. So we'll start with the block when we apply Newton's second law. So to this end, we'll just write here block. We're going to use sum of the forces. It's equal to M2 R2 double dot. And that's equal to, we have T1 in the vertical J direction, or the positive J direction, minus M2G in the J direction. That's all the forces, and then this is going to be equal to minus M2 Y double dot, and that's the acceleration of this block, and that's also in the J direction. So from here, we can go and we can solve for T1, and T1 will be equal to M2 times G minus the quantity G minus Y double dot. From there, we're going to go on to the pulley. To sum of the forces equals M, just say R3 dot. We didn't define an R3 or R3 double dot. We didn't define that when we originally did our acceleration vectors, but this is just 0 in both directions, all three directions actually. And so from here, this just becomes a static problem. In the vertical or in the horizontal direction, we're gonna get R2 minus T2, the I direction plus R1 minus T1 minus M3G. In the J direction, that's equal to 0. We'll just say 0I plus 0J. And so then we'll find then that R2 is equal to T2, and then R1 is equal to T1 plus M3G. It doesn't really give us any more information regarding the motion of the system, but we were able to at least find those reactions. So we're going to want to go then and do some of the moments. In this case, we're going to sum them about the origin, which is the pin position of that pulley. And this is going to be equal to the moment of inertia I times the angular acceleration alpha sub p of that pulley. And for this problem, we said that the moment of inertia is just I. We did not. So this is some special pulley that has some weird moment of inertia, and we're just calling it I. Rather than treating it like a disk and then computing it that way, we're just saying it's I. Okay, so in this case, the sum of the moments is going to be equal to R in the I direction crossed with minus T1 in the J direction plus R in the J direction crossed with minus T2 in the I direction. And we don't need the reactions or the force due to gravity because they're all at the pin position or the point that we're summing moments, so they produce no moment. And then this is equal to minus I times V double dot. And that's in our k hat, the k hat direction. From here, we'll end up with the quantity minus R times T1 plus R T2 in the k hat direction equal to minus I V double dot in the k hat direction. I changed my mind. Instead of using I, we're going to actually use the moment of inertia for a disk. And I happen to know that, so I'm going to write that out. So this is then equal to minus M3 R squared over 2. It's that's the mass moment of inertia for a disk. This is phi double dot in the k hat direction. So from here, let's go ahead and substitute in for T1. So this is going to be R M2 minus R M2 G minus Y double dot plus R T2. We're going to drop the K hats because everything's in the K hat direction. We'll get minus M3 R squared over 2. Phi double dot. And now we'll be able to solve for T2. And we'll find that it's not equal directly to T1 because we've got some inertial term due to the pulley. Okay, so from here we solve for T2. And T2 will be equal to minus M3 times R over 2 times phi double dot plus M2 times the quantity G minus Y double dot. Okay, we'll now move on and look at the disk. For the disk, we're going to get some of the forces. It's equal to the mass times the acceleration of the center of mass, or RC in this case. Scroll back up here for a second. Okay, so forces, we're going to get T2 minus our friction force, that's in the I direction, plus quantity N minus M1 G in the J direction. And then this is equal to 3M1 times R theta double dot. And I'll talk about where I got that from in a moment. Okay, so radius of the pulley is 3R. The pulley is, or sorry, not the pulley, of the disc is 3R. Since it's rolling without slip, it is the center, or the instantaneous center of rotation is at the contact point. So this disc is really rotating about this point here, such that, I'll let this go away, the acceleration of the center of mass is going to be equal to 3R theta double dot. Like that. That's where that 3M1, 3R comes from. Okay. That's going to be in the I direction. Okay, so from here we can find that our friction force is going to be less than or equal to mu Sn This is the condition for rolling without slip. N is clearly equal to m1g, since there's no acceleration in the j direction. And so our friction force is going to be less than or equal to mu s m1g. So if slip is impending, then the friction force is exactly equal to the static friction shown here. If slip is not impending, which means like the disc is just about to slip, we've reached the maximum capacity of rolling. If that's not true, then the friction force is whatever. We don't know what it is at this point. It's whatever is needed in order to constrain the motion such that we're rotating about the contact point. Okay, we're gonna go ahead and assume that it's equal to, that FF is equal to mu s m1g. We're gonna go ahead and we're gonna solve with that condition. So then we're gonna get 3 m1r theta double dot is equal to, we're going to substitute in for T2 here. We'll get minus M3R over 2 phi double dot plus M2 G minus Y double dot. And then we'll bring everything with a double dot in it onto the left-hand side. So we'll get here 3m1r theta double dot plus m3r over 2 phi double dot plus m2 y double dot, and that's equal to, so hold on, I left out the friction. On the right hand side in the top equation we should have our friction force, which is going to be mu s m1g, and then in the second equation we're going to get m2g minus mu s m1g. Okay, so now we have one equation and we have three unknowns. The unknowns are theta double dot, phi double dot, y double dot. Because we have rolling without slip, we are now able to create a kinematic relationship between all of these different variables. We also don't need to do some of the moments about the center of mass or about the contact point, although you could if you wanted to. We don't need to do that on the disk because of this rolling without slip. If you have rolling with slip, then you do need to do some of the moments. And at that point, the instantaneous center is no longer the contact point, so you're going to do some of the moments about the center of mass. Okay, so because we're rotating about the contact point right here, the motion at the top, way at the top here, this is going to be equal to 6r theta, so twice the radius, which is 3r, times that angle. That is our displacement up here. The displacement up here that connects here, this is going to be r times phi. And then the displacement going down here, y, that's going to be equal to r phi. Okay, since the wire is inextensible, both the top of the disc and the top of the pulley must both have the same displacement. And so then we'll get 6r theta is equal to r phi. From here we can just eliminate our r, and we'll find that phi here is equal to 6 theta, such that phi double dot is equal to 6 theta double dot. Okay. So we said y is equal to r phi. Again, the wire is inextensible. If it was extensible, meaning there was a spring connecting the two, then this would no longer be true. This relationship between y and r phi. But it is inextensible, so this remains. So here we're going to get y is equal to then 6r theta, and then y double dot will be equal to 6r theta double dot. And from here, we're going to go and we're going to substitute in to our equation that we just derived above. We're substituting for phi double dot and y double dot, and then we'll get an equation for everything in terms of theta double dot. You could choose to use phi if you wanted, or you could choose to find y, an equation for y double dot. Since we have, all of these here are what we would call kinematic constraints. Ran out of space. Because they constrain the motion of the system, hence why they're called constraints. So that means that if you can find an equation for y double dot, and that's an equivalent to an equation for phi double dot, and it's also equivalent in terms of theta double dot, meaning that you could solve any three of those equations, and then you would be able to determine the motion of the entire system, because we have these constraint equations. Okay. So we're going to go ahead and we're going to substitute in here. We're going to get then 3 times m1 plus m3 plus 6 m2. All of that multiplied by r theta double dot is equal to m2g minus mu s m1g. And that's our equation of motion, which we could use and solve directly for theta double dot if we so desired.